Hello everyone. I am Mitali Patel with my team members Ayushi and Tanvi presenting you the idea of signal compression. So in this video we are going to explain you about image processing, signal compression and its implementation. Next I would like Ayushi to continue.
So first, let's look at the definition of signal compression. Signal compression is the process where the redundant information in a signal is identified and deleted. Next, we'll be looking at signal compression is quite an important technology in digital communication. Speech, audio, image, and digital video are all important fields of signal compression, and plenty of compression methods have been put to practical use. But in this video, we will be describing image compression. Next, we'll be looking at the definition of image compression, which is minimizing the size in bytes of a graphic file without degrading the quality of the image to an unacceptable level. Next, we'll be looking at why do we need image compression. So image compression is beneficial because it reduces the amount of memory needed to keep digital files or send them over a network such as internet. The reduction in file size allows more images to be stored in a given amount of disk or memory space. It also reduces the time required for images to be sent over the internet or downloaded from web pages. Next, we will be looking at an example which proves why is image compression required in nowadays. So consider a black and white image that has a resolution of 1000 cross 1000 pixels, and each uses 8 bits to represent the intensity. So the total number of bits required is 80 lakh per image. And consider if it is a video with 30 frames per second of the above mentioned type images, then the total bits will be 72 crores. As we see, just to store 3-second video, we need so many bits, which is very huge. So we need a way to have proper presentation as well as to store the information about the image in a minimum number of bits without losing the character of the image. Thus, image compression plays an important role. Next, we'll be looking at the applications of image compression in real life. So the areas where image compression is used are in television broadcasting, remote sensing via satellite for military communication system through radars, then teleconferencing systems, weather reporting applications, and geological surveys. Now I would like Mitali to continue.
So here we'll come across the idea of types of signal compression. So signal compression is the use of various techniques to increase the quality and the quantity of signal parameters transmitted through a given telecommunication channel. So the first type is bandwidth compression. Bandwidth compression implies a reduction in normal bandwidth of an information carrying signal without reducing the information content of the signal. Second is the data compression. Data compression, also known as source coding or bitrate reduction, is a process of encoding information using fewer bits rather than original representation. Third is the dynamic range compression. Dynamic range compression, or simply compression, is an audio signal processing operation that reduces the volume of loud sounds or amplifies quiet sounds, thus reducing or compressing an audio signal dynamic range. Fourth is the gain compression. Gain compression is a reduction in differential or slope gain cause, while non-linearity of the transfer function of the amplifying device. Fifth is the one-way compression function. One-way compression function is a function that transforms the two fixed length inputs into a fixed length output. Sixth is the image compression. Image compression addresses the problem of reducing the amount of data required to represent a digital image. Here, in this video, we will look in detail about the techniques and its implementation. Next, we have the steps involved in compressing the image. So first, we'll take an image as an input. After that, the image will be we will process the image in the encoder. The encoder have two parts, that is source encoder and a channel. After that, the image passes through the channel and it reaches the decoder. In the decoder, we have channel decoder and the source decoder, and finally we get an output. Next, we have image compression techniques. The image compression techniques are broadly classified into two categories depending whether or not an exact replica of the original image could be reconstructed using the compressed image. So the techniques are lossless compression and lossy technique. Next, in the lossy compression, it is also known as irreversible compression, is the class of data compression method that uses inexact approximation and partial data discarding to represent the content. Lossy compression algorithm are techniques that reduce the file size by discarding the less important information. Computers can capture an incredible amount of detail in a photo, but how much of that detail can humans actually perceive? As it turns out, there is a lot of detail that we can remove. Lossy compression algorithms are all about figuring out clearly or cleverly ways to remove detail without human noticing. So here in this figure you can see that for figure A depicts the original image and the figure B is the same photo but it's compressed half of its size. Next is the lossless compression. Lossless compression is a class of data compression algorithm that allows the original data to be perfectly reconstructed from the compressed data. Here, the examples of lossless compression is a PNG, text compression, or zip, or broadly. Here, lossless compression methods are reversible. Lossless compression is used in cases where it is important that the original and the decomposed data be identical and where deviations from the original data would be unfavorable. Next, I would like Tanvi to continue.
When should we use lossy and lossless compression? Lossy compression data is good for basemap imagery because it has faster loading speeds with lower compression ratios. You should not choose lossy compression if you want to perform further analysis of the data. Lossless compression is good if there will be a new analysis of the data. This is because it doesn't alter any of the original values. This means that it's good for discrete data or any raster image that already has lossy compression. Next, I would like to show you a demo of image processing implementation using FFT in MATLAB. Here is the code. In this code, first I have inputted the image, then I have converted the image into grayscale for better illustration. I have calculated the size of the image by using the function size built in MATLAB. Next, we are showing the original image. Then we are taking FFT of the grayscale image. And then we are sorting the grayscale image in we are sorting it we are taking the absolute values of the grayscale image and sorting it according to increasing order and converting into a vector form. Here in this loop, we are finding the compressed image to 99%, 0.5%, 1%, and 0.2%. Here first we are finding the threshold based on the sorting vector which we have found. In here we have next we are finding the small indices. Then we'll calculate the threshold of the small indices, and then we'll convert it into the compressed image using IFFT, which is inverse IFFT, and then we'll print the image. Here I would like to run the code. First we'll get to see the original image. Next we'll have 99% compressed image, which is not much different than the original image. Then we'll have 5%, 1%, and 0.2%. As we can see, 0.2% compressed image is quite different than the original image, whereas 1%, 5%, and 99%, 99% does resembles the original image very much. Thank you.